I'm really, really pleased that Bob accepted our invitation to talk, and Bob will now talk to us on the theme of using the environmental sciences for a sustainable future. Bob Watson, thank you very much.
Thank you. What I wanted to today is actually talk about two big issues, climate change and biodiversity loss, and talk about what the relationship is to four critical issues: food, water, energy, and human security. So it's a very quick run through. It's a very broad talk, no depth whatsoever, but it's a broad talk about what the issues are. First, I think we have to realize is that we have a series of big environmental issues that fundamentally are often thought about in isolation, both by the academic community and certainly by the policy community, and yet they're completely and utterly interrelated. We can't think of climate change without thinking about how climate change affects stratospheric ozone depletion, or biodiversity, or air quality, or the forest. Equally, we can't think of climate change without understanding how changes in forests affect climate change, how changes in stratospheric ozone affect climate change, how air quality or desertification affect climate change. It's one fully integrated system which we need to understand the scientific linkages, but even more important, we have to understand the policy interlinkages. There's no point having a policy to try and protect climate change if it has an adverse effect on biodiversity or on air quality or water. A perfect example of a not very well thought through policy was using biofuels to replace fossil fuels. Now, biofuels make eminent sense at one level. They can actually replace fossil fuels, good for the climate system. They can reduce greenhouse gas emissions. They can help us on energy security, and they can effectively help on rural development, another commodity for the farmer to sell. But the way we're generating biofuels today of using food for fuel, in my opinion, is a highly misguided policy in many respects. There are some sustainable biofuels, economically, environmentally, and socially, but there's also a large number that are not sustainable. And so we have to understand the interrelationship between all of these various issues. Now, there's absolutely no question that climate change, loss of biodiversity, and ecosystem degradation are key issues. They affect the economy, loss of natural capital. They affect poverty alleviation, the livelihoods of the poor. They affect human health, and they affect security at the personal, national, and regional level. There's actually no question these issues are both inter- and intra-generational equity issues. Developing countries and poor people in developing countries are the most vulnerable. But it's us in the rich countries that primarily cause the problem. Also, the actions of today will affect not only our children, our grandchildren, but future children after that. So there's a major equity issue. Our children and grandchildren in 2050, if we don't deal with climate change today, if we don't deal with the loss of biodiversity today, they will ask why were we so greedy to want cheap energy, cheap resources, and not think about their future. And so on climate change, where are we? We clearly need to have a strategy that both mitigates climate change and adapts to climate change. The climate is already changing, and future change is absolutely inevitable. We cannot stop it, but we can limit it with good mitigation policies. We need to look at the production of energy, the use of energy, the way we manage our land. But we've also got to realise there's a poverty issue here. The economy is driven to a large extent by the use of energy, and therefore, as we move forward in the future, the question is how can we transition to a low-carbon economy cost-effectively for developing countries? Over 1 billion people have no access to modern energy. They need access to modern energy to grow. So there's a major poverty issue embedded in mitigation. In adaptation, it's absolutely clear. We are totally and utterly maladapted to today's climate variability in most sectors, in most countries of the world. We have perverse policies. We subsidise water, or we don't pay for water. We subsidise agriculture. We subsidise the energy system. So the first challenge is how to integrate climate variability into policies today so we become more resilient to today's climate variability, and then we can deal with the projected climate change in the future. So there's a real issue of mainstreaming climate into all sectoral and national economic policies. There's no doubt, and I do mean no doubt, we humans have changed the composition of the atmosphere. Greenhouse gases such as carbon dioxide, methane, nitrous oxide, fluorine-containing compounds. There's also no doubt the Earth's climate has changed. And most of that change, especially in the last 50 years, cannot be ascribed to natural variability. It can only be ascribed to human activities. In addition, the observed changes will continue into the future. We've seen warmer temperatures. It will continue to warm. We've seen changing precipitation patterns, not only spatially but temporally. More heavy precipitation events, less light precipitation events. We've seen increase in sea level. We've seen mountain glaciers retreating. 60,000 mountain glaciers across the world are retreating, and most will actually disappear in the next 10, 20, 30, 40 years. Major implications on local communities that depend on snow and water runoff from those glacial systems. We're seeing a melting of the Greenland ice cap at a rate we can't explain. Reduced Arctic sea ice, both the extent and the thickness in summer. More frequent extreme weather events and more intense cyclonic events. I've been told this doesn't really show, but what we see down at the bottom here are effectively the global surface temperature, global land temperature, global ocean, and then you see it broken down by region, so Europe, Africa, South America. The black line are the observed temperatures, surface temperature. The blue line is actually trying to simulate the observations with very sophisticated climate models, assuming the only things that have changed are natural phenomena, changes in solar radiation, changes in volcanic activity. And as you can see, the blue line does not simulate the black line in any one of these various diagrams. The purple line is again an ocean-atmosphere coupled climate model which tries to simulate the past using not only changes in natural phenomena but changes in human activity. The increase of greenhouse gases, which warm the atmosphere, the increase in sulfate and other aerosols that can actually cool the atmosphere, changes in land albedo, changes in stratospheric ozone, and as you can see, the purple line does a very good representation of the observations of the last 50 years. And it's this type of information and much more that has led us to say that most of the observed warming in the last 50 years is due to human activity. So that's the past. But what we obviously care about is the future. We don't know what the future will be. What will the future emissions of greenhouse gases will be? They'll be dependent on demographic change, number of people, family size, rural to urban migration. They'll depend on economic factors. What's the rate of growth of the world's economy? How does the trade system work? It will depend on choice of technology. It will depend on socio-political factors. Will the world work together to be a more sustainable world? Or will it be a fortress world, a fragmented world, as we've seen, let's say, in many of the last 8 years under a certain presidency across the pond? What will the cultural issues be? How will we as individuals behave? Will we try and maintain resources, or will we squander them? So we don't know what the future will be. So we do plausible futures. We mix and match those variables, and we come up with projected changes in greenhouse gas emissions. We convert that into greenhouse gas concentrations, not just carbon dioxide, but also methane, nitrous oxide, etc. And then we can use a climate model to project what could happen to the Earth's climate. This is global mean surface temperature, and what it suggests is over the next 100 years, from the year 2000 to 2100, the Earth's climate will warm an additional 1.4 to 6.4 degrees Celsius, on top of the 0.7 degrees Celsius we've already seen. So relative to pre-industrial period, 1850, we'll have seen roughly a 2 to a 7 degrees Celsius warming if we don't get to grips with our greenhouse gas emissions. But the world doesn't warm uniformly. It depends on latitude, it depends on longitude, it depends on season. So what you see here is 3 greenhouse gas emission scenarios, low, medium and high, for the decade of the 2020s and the decade of the 2090s. And as you can see on the decade of the 2020s, those maps of the world all look the same, and they are.